Okay, so this presentation is going to be for the lab, Gravitational Forces and Energy. The lab handout that you should have gotten looks like this one in class. And our objective here is to basically determine the gravitational field of various objects, starting with the Earth. And then we'll look at a number of different objects that there's a data table for here, looking at the Earth and then the Earth Moon system, looking at the gravitational field of the Moon, Mars, Jupiter. And then ultimately we'll look at the sun and a star, which is about 17 times the diameter of the Earth, Regal A. 17 times the mass of the sun and 62 times the radius of the sun is its mass and radius. So in the data table here, we're going to have these celestial bodies that have their mass and radius indicated. And our goal is to find the escape velocity, which is how fast you need to be moving from the surface, and the escape energy per 0.01 kilograms of matter to escape fully from the gravitational field. So at the surface, you need to be moving at a given amount of speed to be able to get out of that gravitational field. And for a black hole, as I'm sure you've all heard of before, black holes have escape velocities at their event horizon that are equal to the speed of light. So that's why we have the escape velocity, the speed of light. And really, it's just an exercise in futility to look at the escape energy for a given amount of matter, because the ability to make matter that has mass escape from a black hole is impossible, because actually light can't escape from a black hole either. And that's where the model, Einstein's model of gravity, comes in that unlike Newton's model of gravity, which models it as a force between two masses, Einstein's model of gravity suggests that light can interact with the gravitational field. So the fact that light actually redirects in a gravitational field and is bent by a gravitational field is something that Einstein's general theory of relativity describes. So we're not going to really get into the math behind that. We're just going to look at, the implications for how we can create black holes. And we're going to look at this slideshow now just to get an idea of how we're going to model gravitational fields. So this simulation is going to use the law of universal gravitation to gain perspective on planets, moons, stars, and black holes. Our first video that we're going to watch is star size comparison. So I'm just going to click on that and allow you to view it through my screen. And it just plays some music in the background so I can talk a little bit over it. But you'll see it's only about 2.5 minutes. So we start off with the moon. It's going to just show increasingly large objects through the solar system and give you an idea of the scope of the size of stars that are out there. So the gas giants clearly are much bigger than the Earth. And then the sun is larger than all the other objects in the solar system combined. And that's a relatively small star compared to some of the other big ones that are out there. And as now the sun is starting to disappear from view, as we look at, this is the star Regal, which has 62 times the radius of the sun's radius. And that's still small in comparison to some of the largest bodies that are out there. And of course, the Earth is no longer in view because of that scaling that they do. So the next video does a good job of demonstrating scale as well. It's impossible to imagine something this big. And when we start getting into these numbers and we start talking about big speeds in years, it doesn't really do a good job of perspective, giving perspective on this stuff. But it is what it is. I mean, it would take a long time to travel around it at a high speed because it's so big. And of course, the message of the video is, that we're really insignificant compared to the scope and scale of the universe out there. 100 billion galaxies. Each one of those stars is only one of hundreds of billions of stars. And no, we're not the center of the universe. Okay, funny. All right, so there's that video. And now the next one is called black hole size comparison. And this does a good job of demonstrating kind of different powers of 10, but it really introduces the concept of a solar mass, which is a body that has the mass of a sun is one solar mass. One sun is one solar mass. Whoa, lost it. Hold on. Okay, so hold on, let's back this up just a tad. So Einstein developed his relativity theory, the general theory of relativity, his model of gravity. He saw his equations also contain something very strange. It would be able to stop time, possess infinite gravity, and possibly destroy space itself. So he's talking about mathematically, when you run the equations to bigger and bigger masses, that some other variables get out of whack. And he thought there was something in place that would stop this from happening, but it turns out that there is the possibility of a black hole, and there's many of them. So this is an important definition, and that is that you can take an object, and if you squash it small enough mathematically at its surface, since the Newton's universal gravitation equation has this radius in the denominator. So just bring up that formula for the law of universal gravitation again. If this radius, oops, get back. If this radius gets small enough for a given mass, the force of gravity will get infinitely big. So what that's saying is that any object can get squashed to a small enough radius that its mass will be sufficiently large. If it overcomes this tiny value of the universal gravitational constant, it can turn something into a black hole. It can raise the acceleration due to gravity above where the escape velocity is going to be the speed of light. So now that's called the Schwarzschild radius. So take the sun, shrink it down to a small enough area. Now, the physics of what's going on inside the sun prevents this from happening, but it can expand and contract as it's a gas. It can get squashed closer together or spread farther apart. In fact, a lot of people know that it's going to expand and eventually be big enough to where it's going to consume the Earth. So it's kind of an academic idea to squish something down to a smaller and smaller size, but eventually it'll turn into a black hole. And the Schwarzschild radius is the size that that mass would need to have in order to be a black hole. That's what the Schwarzschild radius is. So this is going to demonstrate that right now. So it's now the size of Earth and going. Right around the size of Manhattan, it turns into a black hole. And we're going to calculate that actual size, about the size of a peanut for the Earth. So this is talking about a stellar black hole with a mass that's comparable to the sun, 3 to 4 solar masses. It's one of the smallest known black holes out there. Now, a black hole that's the size of Mars or our moon. And this is going to demonstrate how much material it would take to make that happen. And it's about a 1,000 solar mass black hole. So the event horizon for 1,000 solar masses would be about the size of Mars. That doesn't mean there's a surface. In fact, they believe that inside the black hole is empty space, and that at the center is a point of infinite density called the singularity. So it doesn't make physical sense compared to what we're used to in terms of our mechanical thinking. But in terms of what the math suggests and what Einstein's relativity equations suggest, which there's nothing to prove otherwise, it suggests that there's a point of infinite density at the center called the singularity, and that beyond that event horizon, as you travel further in, we have nothing to tell what happens inside there, because that's where quantum mechanics and relativity will overlap in terms of their scale of the forces that they would produce, but there's no model that predicts what can actually happen inside there. That's unknown, and there's no data or evidence that can prove it, because it's impossible to observe because the light can't escape. So that's where our physics is a little bit uncertain, is inside a black hole. People don't really know what's going on inside there. All right, so I'm gonna let the video continue. So we just finished up 1,000 solar mass black hole, and now we're scaling back. And you can notice the scale is going way, way back. So what we're gonna look at now is something called a supermassive black hole. So that's a 1,000 solar mass array, which is then stacked 100 tall. So I think it's actually 100 by 100 by 100 cube. And then that stack ends up being like a billion. And then 20 billion. Yeah. Each of those cubes was a billion. This just gives you an idea of how big a mass is accumulated and forming one of these supermassive black holes, which is still just a tiny speck at the center of the galaxy. So galaxies are hundreds of light years across, meaning the time it takes light to cross a galaxy is like 100 years. So hopefully you found that video interesting. At least gives you a little bit of perspective on what we're going to be doing here. Okay, so those are recommended videos. You can feel free to watch those. They're linked in the PowerPoint presentation. And now I just want to continue with the slideshow. So let's see, from current slide. There you go. So what determines the force of gravity? We already looked at Newton's model of gravitation, which is any two objects will exert an attractive force on one another based on the following: their masses and the distance separating them. Planets and stars have gravitational fields or regions surrounding them where objects accelerate at various rates. The bigger the mass of the planet or the star, and the closer to it you are, the stronger the field will be. Right. So this is our universal gravitation equation, where Fg is the force of gravity in newtons. Our universal gravitational constant we just defined the other day. It's 6.67 times 10 to the minus 11 newtons meter squared per kilogram squared. M1 and M2 are the masses of objects 1 and 2. So Newton's law of gravitation models gravity as a force between two masses. And then the radius is the distance separating objects in meters, for m for meters. All right, so our gravitational field strength decreases with the distance from the surface by the square of the distance. So it's going to form an asymptote to the x-axis, which is going to mean that it's going to basically get smaller and smaller until it's basically zero. It's going to get closer and closer to zero, although it's never really truly zero. All right, because you're always going to have some calculatable value, since you can't divide by number and get zero. Divide by non-zero number and get zero. Now, gravitational potential energy works differently in space than it does close to objects when we assume a constant value of g. The way gravitational potential energy works in space is we assume infinitely far away from any mass or anything that has a gravitational field, you're at zero potential energy. And for any object that you move towards, you're falling into that gravitational field. So as you lose potential energy from zero to some negative value, you speed up. All right. Now you can whip around an orbit and whip out the other side and come out really far away on the other side, without having lost or gained any energy. Your net energy would be the same if you just kind of loop around it and allow that gravity to change your direction. But the idea here is that you have zero. It's kind of like fabric. And imagine the fabric being, the surface of the fabric is at height zero. And then any planet that you go is going to press that fabric down and bend it down, sort of like a large person standing on a trampoline. And as you move down that fabric, you're going to speed up, you're going to gain kinetic energy because you're losing potential energy. And in order to get back out from that gravitational field, you need to have something that does work to you to get you back up to that 0 point, because you lost all that energy in falling towards that object. Right, so you're losing potential energy, gaining kinetic energy as you fall into a gravitational field. To get back out of the gravitational field, you need to be moving fast enough, or you need to have something that's pushing you over a distance like a rocket to lift you out of that gravitational field. So if you're moving fast enough to fully escape a gravitational field, the minimum velocity you can be moving at to get free of that gravitational field and be off to deep space basically at rest with zero leftover energy, that minimum amount of energy you can have is the escape velocity. And it's basically the amount of kinetic energy you need to escape an object's gravitational field. And on the surface of the Earth, there's a formula that you can use to calculate it. It's basically doing an energy balance by saying the total kinetic energy and potential energy at the surface adds up to zero. And then as you get farther and farther away, your kinetic energy decreases and displaces that negative potential energy you have. And, the total escape energy is equal to the kinetic energy you'd need to have when you're moving at the escape velocity. All right, so to find the escape velocity, you can do the math and get this formula. That's what it reduces down to, with no other energy losses, like no friction through the atmosphere, things like that. But for the Earth, 11,200 meters per second is the escape velocity. So if you fire an object upward on the surface of the Earth at 11,200 meters per second, assuming no energy loss to air resistance through the atmosphere, it's going to never fall back down. But if you fire it at a lower speed than that, eventually it's going to stop, slow down to a stop, and fall back down, and it'll return to the Earth. As an object gets more massive, like Jupiter and the sun, the escape velocity gets bigger. As an object's less massive, like the moon, the escape velocity is even smaller. If you're talking about like a comet or something, like a big asteroid, that escape velocity would be small enough where you could kick off with your legs and jump and leave and never return to that object. So there's all different scales of sizes of escape velocities that you can have depending on the mass of the object. And obviously for a black hole, the escape velocity at the event horizon is the speed of light. That's not to say that the object has mass that's in or outside of that escape velocity region. That's just to say that, that there's a point called the event horizon inside of which nothing can escape, because it had to be moving at greater than the speed of light, and it's impossible for an object to travel at a speed greater than the speed of light. So for any object that is small enough to have an event horizon, it will basically be a black hole. And that's where you're crossing into what you call relativistic space, when Einstein's general theory of relativity starts to skew time and starts to skew everything else. Funky things start to happen. So we're going to model it with the equations of mechanics, but it really isn't accurate to use mechanics equations on things in that realm. It only makes sense to use Einstein's equations because they're the ones that deal with that kind of complicated situation of when light distances start to, length doesn't hold up, time doesn't hold up, mass, inertial mass changes. So all these things change when the gravitational field gets really big, and Einstein has a really clear model of how that happens. I'm going to try to give it a little bit of a justice of an explanation. But anyway, the escape velocity of a black hole is the speed of light. So black holes are so massive that their gravitational field will not allow light to exit from its event horizon. At the event horizon, the escape velocity is equal to the speed of light, which is 2.998 times 10 to the 8th meters per second. Right, so we're going to use goal seek, which is trial and error. We're going to adjust the radius of the black hole until we find a point where the escape velocity is the speed of light. And at that location, we'll know that's the event horizon. Everything inside of it is like, so quote, inside the black hole, but everything outside of the event horizon is something that you can see the light from, even though it may take 100 years for the light to travel from some point outside the event horizon out to where you can see it. Even if you're only like a few light years away, it may take hundreds, if not thousands of years for that light to reach you, because in relativistic space, time is skewed, which is where there's all types of interesting things like time travel you can try to talk about. So on the final completed spreadsheet model, the increment of position is 1/5 the radius of the central object. So as you look at a bigger object, just like we saw in that first video where there's objects of different scales, counting by the same increment of position wouldn't make sense, because you would count all day if you're counting in Earth radii and never make a dent in the supermassive black hole. So we count by a fraction of the radius. So we're always counting by 1/5 the radius of the central object. So each layer, each line that's highlighted on the spreadsheet model shows you one object radius above the surface. All right, so I'll point that out when we get to the spreadsheet model. But acceleration due to gravity, weight, and gravitational potential energy on the surface of the central object can be found in the first non-zero row, which is row 10. If you're entering masses or radii that are bigger or smaller than numbers that you can use just English notation, if you have to use scientific notation, there's two possible ways to do it. There's the way that is kind of most consistent with how we've done things so far, and then there's the easy way, which uses the letter E. But you want to enter it as an equation: equals some digit times 10 raised to whatever power. That's 6.67 times 10 raised to the minus 11 power, which is the universal gravitational constant. Or if you just want to enter 6.67 times 10 to the minus 11, scientific notation by default uses this letter E. So you just do 6.67, the letter E minus 11, and the computer will recognize that as 6.67 times 10 to the minus 11. And these two things are equivalent if you enter exactly as they are without the quotation marks. Okay, so for these big numbers like the mass of Jupiter or the radius of the sun, you're going to need to use scientific notation because it'd be impossible to keep track of all the zeros there. And that's where knowing exactly how to do that, the 3 digits of the scientific notation, the letter E, and then the power on the 10, that's the easiest way to do it. All right, so I want to explain the general theory of relativity real quick. Let me just make a blank slide here and use that as my working kind of background, and try to draw like a little bit of an image here that's going to give you an idea of how relativity works. It's basically a model for gravity. And it's Newton's model of gravity that suggests that, so let me make a shape. I'm just going to draw an elevator here. Slow computer. Hopefully it's not that slow and working for you guys, but All right, so we're gonna take an elevator and we're gonna take that elevator and just attach a long chain to it. All right, so I'm just gonna draw it like this. And that elevator that we attach a chain to, up top, something's gonna grab onto that chain and pull it and accelerate it up at 9.8 meters per second squared. All right, so it's gonna be accelerating up at the acceleration due to gravity, 9.8 meters per second squared. All right, so I'm just gonna do as best as I can with the mouse here. Meters per second squared. And all right, so now a person inside that elevator was kind of like blacked out and they didn't know what was going on, but now that they woke up, they feel like they're standing on Earth because they're accelerating it up at 9.8 meters per second squared. Now, this is an elevator that's in deep space, so there's no gravity. G out here equals 0. All right, so if there's no outside gravity, you're far separated from anything that can produce gravity. This person would be weightless. They would be bouncing around inside this elevator. But as a result of being this external being or whatever, you could think of it as like, God is grabbing onto this wire and pulling it such that this person can't see. This person's just in here thinking, boy, it feels like I weigh 9.8 meters. It feels like I weigh exactly what I do on Earth. I have air inside here, and I, the person in the box doesn't know any differently. They step on a scale, and the scale weighs what they weigh. So, if they step on that scale, it's going to have the same weight reading as what it would weigh normally. All right. But what we know as the outside viewer from our reference frame is that they're actually being physically accelerated. They're not in a gravitational field that has a downward rate of acceleration of 9.8 meters per second squared. They're actually being physically accelerated in a zero gravity environment. Now, Einstein suggests that there's no experiment that this person could do to prove that they're not in a gravitational field. And in fact, in making that incorrect assumption that he was present in a gravitational field, he would be accurate in doing that. That's how Einstein modeled gravity. So you can imagine now, if this person was holding a mass in their hand, right, and they dropped it, you could imagine like an apple, like Isaac Newton's apple. They drop the apple and it falls down towards the ground, and they want to measure the acceleration. They hook up a ticker tape to it and it falls down. And as they release it, according to Newton's first law, it's going to continue at whatever velocity the system was moving at the instant that he released it. But as a result of this external acceleration that this thing is being pulled with, the object continues at constant velocity, but the elevator accelerates up at 9.8 meters per second squared to meet that. But to the observer, the person standing there, it looks as if that object's accelerating downward at 9.8 meters per second squared. So Einstein basically did the math to make it work out so that that's how gravitational fields are modeled. And what that predicted that was interesting was that if a ray of light was shining across this elevator and it entered at one side, like through a hole over here, if it was perfectly horizontal, it would hit on this side at a given point over here. And that elevator, if it goes straight across that beam of light, if the elevator is accelerating up at 9.8 meters per second squared, that ray of light wouldn't hit at that exact location. It would hit a little bit below. All right. So if it hits below due to that acceleration, that makes sense as to why that light would bend. The faster the rate of acceleration, the more that target is going to move up and out of the way, and the time it takes the light to bridge itself across the elevator there. All right. So that distance, that gap that it moves across, causes the elevator to move up a certain amount in that amount of time from when the light entered over here. And that, from the observer's point of view, is going to be a bending of the ray of light. But it's impossible for somebody to observe light bending because everybody observes light traveling in a straight line at, the same speed. So it's going to skew this person's perception in such a way that the light's always going to look like it's in a straight line at the same speed. So that's out to an outside observer that the ray of light's going to bend. And for us as outside observers, outside gravitational fields of black holes, we see black holes where light can't escape if the mass is big enough, because it follows that same law that Einstein made it follow for this whole ticker tape experiment to work out inside here, modeling gravity as just an accelerated reference frame. So the whole idea by modeling gravity using relativity is to say that no matter what situation you're in, you're always going to measure the speed of light to be the same thing, and you're always going to measure it to be traveling in a straight line path. And by taking that idea along with making no other assumptions at all, assuming it's possible for time to not travel at a constant rate, assuming it's possible for length to change and mass to change, going with just that one assumption that the speed of light is always measured to be the same in all circumstances, Einstein did the math to basically formulate a model for gravity that we call relativity that works and that predicts that light will bend in this way. Okay, so I'm going to show you how to do the first part of the data table now, because this is going to walk you through similar ideas, this discussion, but you can read this discussion at your leisure. This is going just to show you the equations that we're using: force of gravity equation, gravitational field, little g. There's actually a typo in here. That one mass 2 should not be there. It should just be big G times the mass of object 2. Or times the mass of the central object divided by the radius squared. And then gravitational potential energy is this one, big G mass 1 mass 2 over, that should be over radius. A couple mistakes on these equations here. Shameful. All right, so that's fixed now. No, I don't want to eliminate the R altogether. I just don't want to power on that radius. Okay, so there we go. Those equations check out now. But the procedures walk you through how to code the model, and you're all familiar with that methodology of typing the formula into the specific cell and building the model that way. So once you've completed the spreadsheet model, this is kind of the part that you would pick up. And that is to say that there needs to be a mass in cell E2. So for some of the questions, it may ask you to use a specific mass, but otherwise it's just any mass will do. So I figured, why not put Jordan Burroughs' wrestling weight when he won the gold medal in the Olympics, and that was 74 kilograms. So I'm going to go ahead and open the spreadsheet model, and in E2, the object mass, that's going to be 74 kilograms. That's the mass of Jordan Burroughs. But the central object mass, that for this example is the mass of the Earth, which is 5.98 times 10 to the 24. And notice it reads that, but I would type 5.98, the letter E, 24, and that's going to give me 5.98 times 10 to the 24. So, that's how you're going to enter these big numbers. 6.37 E6 is 6,370,000 meters. All right, and that's the data for the Earth. So for that, we're going to, whoops. Where are we here? Let me X that out. All right, so here's the Earth mass and radius, the escape velocity and escape energy. I'll show you how to read that for the Earth, and I'll show you how to change up those numbers. All right, so the escape velocity is right here, and the escape energy is right up here in F2. All right, so to calculate the escape velocity, that's just equal to the escape velocity from the location on the surface of the Earth. Now, this is the surface right here, and then one full radius above the Earth is going to be right here. You can see that it counts by the increment, which is 1/5 of the radius. Okay, so this position increment right here is 1/5 the central object radius. It's just d2 divided by 5. And in the position column here, it counts up by that increment so that we're at 1, 1.2, 1.4, 1.6, 1.8, 2 radii, 2.2, 2.4, 2.6, 2.8, 3 radii. So right here is 3 radii above the surface of the Earth. All right, so by Earth radius, we just mean we're counting by increments that are equal to the radius of the Earth. And, you know, if I really wanted to have a shape in here that would kind of demonstrate that, then I'd be looking at a circle that is centered, that's centered on the surface there, and a little bit smaller than that actually. So it would have it set starting like, you know, so the center of the Earth right here, and then 1 full radius above it would be right there. All right, so the surface of the Earth is right here, and then 1 full radius above it would be, you know, this distance right here. All right, but I have to move this shape. I can't move it up, but you get the idea. If I had, here we go, I'll just move this to where, don't do that.
No.
There we are. Okay, so this row is the surface of the Earth, and then that's 1 full radius above it. That's 2 radii above it, which is 1 full diameter above it. So it kind of would work out like that, to where you're looking at the surface of the Earth in the first position there. But I'm just going to clear that out because, you know, we don't need all that stuff in the way. We're just going to imagine that. And for the sake of answering the questions here, the escape velocity would be 15,250 meters, which you would type here, 152. I'll throw the commas in so I can see more clearly, meters per second. Or I think actually it shouldn't be that. Yeah, that's just a calculation. Yeah, the escape velocity is right here. That's the 11,200 meters per second. So yeah, I don't know where that 15,250. Actually, that was one of the problems. 15,250. That was just a piece of information from there. Looks like I have some scratch work in here in different places where you may or may not, you know, want to look at those numbers. They're probably going to distract you. But the escape velocity right here is the escape velocity from that location. And as you get farther and farther up, it takes less and less velocity to escape from that location because you're already climbed your way, you know, 1 full radius above the surface of the Earth. So now, or 1 full diameter above the surface of the Earth would be right here. So you only need 6,460 meters per second of velocity to get away from that position, where at the surface you need 11,190 or 11,200 meters per second. So again, you don't need the units if you got the units above in the top of the column. Now the escape energy, that's in kilograms of rocket fuel, and that's 15,440, and that's per kilogram. All right, so you know, or per this 74 kilogram mass. So to get a 74 kilogram mass escaped from the Earth's gravitational field, it's going to take you 1,544 kilograms of fuel to do that. So it's very costly to get an object lifted off the surface of the Earth. That's why there's big bucks in, you know, the rocket business. Ask Elon Musk. All right, but if you look at this energy to get there column, that's telling you how much rocket fuel it's going to take to lift that 74 kilogram mass up. And that's net energy. That's not accounting for the spaceship and not accounting for lifting up the other fuel. That's just the net pure kinetic energy. It does account for the efficiency of the rocket fuel, but it doesn't account for, you know, the full quantity of material that you're going to lift up a 74 kilogram mass person. You're going to have a vehicle that's going to house them. You're going to have the structure of the rocket as well. So there's lots of other things that are going to add to the fuel mass that you're going to need to lift up all that extra stuff. And that's why they drop off the rocket boosters when they launch something into space as well, because those rocket boosters are heavy and they take a lot of energy to lift off. All right, so hold on, let me just get my my plug fixed so that I don't lose my okay, there we go. So I've got a charge still going here. All right, so anyway, I hope that explains each of these columns. The force of gravity is in newtons, the gravitational potential energy is in joules, the acceleration in meters per second squared. And to complete this data table, just show you how to change an object. So the 17 SM, I'll explain that one so that you can do the others and the supermassive black hole as well. I'll explain those. Some of these do get a little tricky, so I'm probably gonna have to work through most of them with you. But again, we'll be able to do some of that on Wednesday. I'm gonna demonstrate how to do more of them. But to do the 17 solar masses, it might help you to put the mass of the sun here, 1.99 E30. All right, so that's the mass of the sun, 1.99 E30, and the radius of the sun is 6.96 E8, 6.96 E8. All right, and now if I want to do 17 solar masses, I can just do equals 17 times the mass of the sun, enter. And if I want to do 62 solar radii, I can do equals 62 times the radius of the sun, enter. All right, so now I've got my Regal A. This is going to give you the escape energy for, now it asks for the escape energy for 0.001 kilograms of matter. So I'm going to have to change out Jordan Burroughs with 0.001 kilograms. That's 1 gram of matter. So that gives you an idea, 17.4 grams of 1 gram takes 17.4 kilograms to lift off of a star like that. It's a very large amount of energy. The only thing that's really going to escape from a star is going to be like a solar flare or coronal mass ejection that's going to pull material away. But the escape velocity is only 323,000 meters per second, which is actually much smaller than the escape velocity of the sun. So the escape velocity for Regal A, if you wanted to record that, it would be 323,300, and you can always round. You don't need to take all those places, or 400 if you want to round to the hundreds place. But for the escape energy in kilograms of rocket fuel, it'll be 17.43 kilograms. But for the sun, if I just had the radius equal to the mass equal to the solar mass and the radius equal to the solar radius, it would be a bigger escape velocity, be 617,589. So 617,590 would be the escape velocity of the sun, and then 63.6 or 63.57 kilograms of rocket fuel to escape. Where to escape from the Earth, that same amount of mass, let me just undo back until we have the data for the Earth in there. Oh wait, let me redo that. I want to leave those. I'll leave those there. All right, but the mass of the Earth are 0.001. Notice it only takes about 20 grams to allow 1 gram to escape. All right, so 0.0208 kilograms or 209 kilograms of rocket fuel to lift off 1 gram, 0.001 kilograms. So the last thing that I wanted to do is look at a few of these questions. So again, you don't need the escape energy. This is impossible. And so is this. But if you wanted to check out the black holes, the way you know something's a black hole and you can turn anything into a black hole is I'll show you with turning the sun into a black hole. All right, which we saw in the video. I'll do the same to the Earth. Okay, so what we want to do is we want to look at the escape velocity there and set that to be the speed of light. So for reference, I'll write the speed of light above it. It's 3e8, which is equal to 300 million. So that's 300 and then 6 more zeros for million. 1, 2, 3, 4, 5, 6. So it automatically defaults to scientific notation. If I just make it a number and I keep the decimal point, 1 decimal point there to show you where it's located, 300 million meters per second looks like that. So I want this escape velocity to be the speed of light. So I can actually use a function in Excel called goal seek. Now you could use trial and error and manually test. I know the radius of the Earth needs to get smaller. It needs to be about the size of a peanut. So let's start off with it at 100 meters. And you'll see the escape velocity is about 2.8 million meters per second, which is about 100 times too small. So I'm going to shrink it down to 1 meter. And now we're at 28 million. All right. So I still got to get smaller. So I'm going to go to 0.01 meters. And now we want to just mess around with that central object radius until we get exactly the speed of light as our escape velocity. So for that, I can do data, what if analysis, goal seek. Now there's a function with an add-on in Google Sheets called solver that you can use. But if I want to set that to be 3e8, I want to do it by changing the central object radius. And when I do that and hit OK, it tests all different values until the escape velocity equals the speed of light. And that leaves behind 8.86 times 10 to the minus 3, which is just under a centimeter or about the size of a little peanut. And that's about the size 8.8 millimeters or 0.00886 meters. That's about the size of the Earth as a black hole, like it was suggested in the video. Now it said the sun was about the size of a small town in the video. So if I take the mass of the sun and I call it that, and the radius of the sun, I'm going to keep it as a number. I'm not going to type it as a formula. 6.96 E8. All right. Now I want to change that radius until I get the escape velocity equal to the speed of light. So again, I'm going to open goal seek. What if analysis? I'm going to set that cell to be the speed of light, 3e8. Do so by changing the central object radius. And what this will do is this will shrink the radius of the sun down until the escape velocity at the surface, quote unquote, which would be the event horizon, is the speed of light. So I say, okay, and you'll watch that number vary until it hits its target value of 300 million meters per second. And in order to do that, 2.95 times 10 to the 3 meters, or about 3 kilometers in radius, which is about 6 kilometers, maybe 2.5 miles across, is the diameter of the sun as a black hole about the size of a small town. All right, so this spreadsheet gives you a lot of ability to experiment with rocket flight, with black holes, and just looking at gravitational fields in general. So what you'll want to do is you'll want to fill out the rest of this data table and then go on. There's no development questions on this one, and you just want to go through each one and answer each question. There's a test for those of you who doubt the story of the moon landing. You can test and see that landing on the moon and launching back off actually didn't take all that much fuel. So in doing a lot of these, some of them are going to take a little bit of time, and some of them are not easy. So I'm going to say for those of you who did the homework set already, I can knock off probably like the last 3 or 4. but actually we just did this last one, number 12. We just got the Schwarzschild radius of the Earth and the sun. All right, and for Regal A to do the same thing for that one, just so you can see that this data is something that I just want you to draw some conclusions for. We saw the data for the sun, but we'll compare the sun to Regal A right here. And when the star runs out of fuel, it's going to gravitationally compress down until it forms a black hole. So what's the radius of Regal A going to be if it forms a black hole? I can make this 17 times the mass of the sun. And this one is going to equal 62 times the diameter of the sun. But when we want to shrink it down, so just to confirm, it does have the appropriate escape velocity there. But now when we shrink it down, we're going to, basically, it doesn't matter what the radius starts at. If you want to turn it into a black hole, all that matters is the starting mass. It has a mass that's bigger than that of the sun. So if we set the escape velocity to be the speed of light, 3e8, by changing the central object radius, it gives me a hard time because it's a formula in there and it needs to be a numeric value. So let me just change it to 4.32 E10, exactly what it started at right there. And now it's a number instead of a formula. It'll let me do goal seek. So I'm going to set that value to 3E8 by changing the, set the escape velocity to be 3e8 by changing the central object radius and hit OK. And that will eventually reach the correct value when the central object radius is 5.01 times 10 to the 4th meters. So Regal A forms a bigger diameter black hole than with the sun because it has a bigger amount of material to start with. So it has like a bigger size as its event horizon. All right. But as far as, the difference in the, why is it having a smaller escape velocity than the sun, which is smaller in mass? That's because it's very hot. And being very hot, it's giving off blue light that's hotter in temperature than the yellow light that the sun gives off. Being so hot, it's expanded to begin with. And that expansion of the gases kind of lifts up off the surface. It creates a bigger separation between an object on its surface, if there was a surface, and its center, which the distance in universal gravitation equation is squared. So being farther away from the center of Regal A, the effect of that increased distance is the reason why the escape velocity is smaller. Okay, so anyway, some of the other questions here about this black hole, it's a little wordy, but basically it's just asking you, is this number 1.17 times 10 to the 13 too big or too small? And it's too big if the escape velocity is greater than the speed of light. It's too small if the escape velocity is less than the speed of light. Hold on, let me just make sure that's right. If the estimated radius is too big, then the escape velocity at that location will be smaller than the speed of light. If the estimated radius is too small, then at that location, the escape velocity will be greater than the speed of light. So for it to be just right, the escape velocity has to be exactly equal to the speed of light. All right, so all the other problems you should be able to work through. It's just a little bit of problem solving. Again, the one with the moon as the central object, where you have the mothership that's orbiting a certain distance away, and the cost of the fuel to lift off to the height, that 2,000 kilogram escape pod that needs to return to the mothership to an altitude of 15,250 meters, figuring out the energy to get there by looking at this, spreadsheet. You're going to have to use the energy to get there thing, and you're going to have to count by whatever increments. You're gonna have to do a little bit of problem solving, but we'll work it through on Wednesday. If you get stuck, this is gonna be due on Monday. And as far as everything else is concerned, hopefully this lab is interesting for you and is a good way to learn about the mathematical nature of the force of gravity and how there is a lot of math in physics, but you can still, without quote unquote doing the math, get an idea of those fundamental mathematical relationships. So you can see, let's just go back and look at the basics of the Earth. 5.98 E24 is the mass of the Earth, 6.37 E6 is the radius of the Earth, and you'll see 9.8 times 10 to the minus 3 is the force of gravity on a 0.001 kilogram mass. If I just put a 1 kilogram mass in there, 9.8 is the acceleration, and you'll notice that the force of gravity and the acceleration due to gravity, it actually goes down by a factor of 4 when you go one radius above, because doubling the distance from one radius to 2 radii is going to decrease the force of gravity by that value squared. So if you increase the distance by a factor of 2, it's going to decrease the force of gravity by a factor of 4. That's the inverse square law. If I triple the distance from the Earth, so I start at 1 on the surface of the Earth, that's 1 radius above the surface, and I go to 2 radii, 3 radii from the center of the Earth, that would be 2 radii above the surface, would be 3 radii from the center. All right, but the force of gravity at that location should be, if you increase the distance by a factor of 3, it should go down by 3 squared, which is a factor of 9. And if I take the force of gravity at the surface of the Earth and I divide by the force of gravity 2 radii above the surface of the Earth, which is 3 radii from the center of the Earth, I get 9. So the force of gravity at the surface of the Earth is equal to whatever the force of gravity is at that point. All right, force of gravity divided by itself is 1, right? But if I divide the force of gravity by the force of gravity 1 full radius above the surface of the Earth, that's double the distance, I get a factor of 4. And if I triple the distance, that's 2 full radii above the surface of the Earth, I get a factor of 9. All right, so here the distance is 1 radius above the center of the Earth. Here it's 2 radii above the center of the Earth. Here it's 3 radii above the center of the Earth. Add a fourth, all right, so 3.2, 3.4, 3.6, 3.8, 4.0, a distance of 4 radii from the center of the Earth at that location. If I just highlight that, so the force of gravity at that location should be 1/16 of what it is on the surface of the Earth. And I can double check that, equals the force of gravity at the surface divided by the force of gravity 4 radii above the center. The surface is 1 radius above the center of the Earth. So 2 radius, 3 radius, 4 radii above the center of the Earth. If I divide those, I should get a factor of 4 squared, which is 16, and 1.6 times 10 to the 1. Of course, if you put that in number notation, it's 16. All right, so if I go to a 5th Earth radius, 4.2, 4.4, 4.6, 4.8, 4.8, 5.0, right there, that should be 25. All right, so if I do the force of gravity at the surface divided by the force of gravity at that location, I should get 25. And of course, I get 2.5 times 10 to the 1, which is 25. All right, so same format. All right, so this gives you the factor by which the force of gravity decreases as you are 1, 2, 3, 4, and 5 Earth radii above the center of the Earth. The force of gravity goes down by a factor of 4, 9, 16, and 25. It goes down by the square of the distance away from the Earth. All right, so that's the distance from the center of the Earth, not the distance from the surface of the Earth. The distance from the surface of the Earth to the center of the Earth is 1 Earth radius. The distance from the center, from 1 radius above the Earth to the center of the Earth is 2 Earth radii. The distance from 2 full radii above the surface of the Earth to the center of the Earth is 3 Earth radii, and so forth. So it can be a little confusing if you're looking at the distance from the surface, the distance from the center. We always measure distance from the center of the object. All right, so with that, I'm going to leave you go to answer the rest of the questions. You have a copy of the spreadsheet on Canvas, and you should be able to email me with any questions or problems you may have. All right, so good luck, and hopefully you enjoy working on the spreadsheet model rather than having to code it. I'm going to go ahead and log off. So you guys have a good rest of the day. And I apologize again for not being able to do this in person, but it's for all of your safety. All right. So have a great one. And I'll see you all on Wednesday. Well, post the Zoom in Canvas and we'll be good to go.